So here's our next problem. We have a wheel that appears to have a spool on it. So there's some rope wound around here, and it's coming off there, and somebody's pulling on that rope with a 5-pound force. All right, then the outer part here is the wheel, and so it's called a spool, so that's certainly spooling there. So the spool is 30 pounds with a radius of gyration. Okay, starts from rest. Here's 5 pounds being exerted to put tension on the rope coming off the spool, and that happens for 4 seconds. So we have roll without slipping. Here we're rolling at A, and so the question is find angular velocity of this device at 4 seconds. So we have speed and time. It looks like momentum. All right. Now, the problem here is that if we're looking at how to handle this problem, we don't know anything about the force of friction. We don't know mu. It's rolling without friction, so the mu s would be the appropriate thing to know here. But then again, do we have mu s times n? You only have as much friction there as you need, up to a maximum of mu s times n. So friction is a very unknown commodity here. So that can be a bit of a problem for us. So I'm going to get rid of this as a variable by, this is a momentum problem. This is rotating, so we're going to use angular momentum. And I'm going to take the angular momentum at A, all right, which is an instant center relative to the rolling. So that seems like an appropriate spot. But by doing that, when you take the sum of moments about A, force of friction is wiped out. So we're using angular momentum. Whoops. Starting from rest, so momentum at the start is 0. External moments about A. All we have is this 5-pound force relative to A. That would go clockwise, so that'll produce a negative moment. And then we have HA for this device. Now what will we expect? G is translating, all right, as it rolls. G doesn't go up or down, it just goes along. Or, depending on what this force does, it goes along that way. But G is on a line. It's translating. While the body itself rotates. Okay? So, we're going to have two terms there. So here is the external moment. This is 0.3 feet radius. Here's 0.9, so there's 0.6 feet in there. 0.6, the force is 5, the time is 4 seconds. And it's clockwise, you get a negative. All right, over here, relative to rotation, we would have IG times omega. All right, so IG would be mass times radius of gyration squared, 0.45. Okay, which we know that. And then after that, we're left with R from A to G cross mass times velocity at G. And I have this right here. A to G is 0.9y cross mass 30 and 32.2. And this would be VG is simply omega cross R. Okay, so if omega was going counterclockwise, this would give us, G would be going in the negative x direction. R is 0.9 feet, so we get minus 0.9x. Now if omega is clockwise, omega would be negative, but that would make the velocity in the x positive. All right, so if here we have, you can see where that came from, and it reduces down to that. But once we're here, we just have one variable, or one unknown, and so that's just a quick, straightforward computation. We get omega is minus 12.7 radians per second. So omega is going this way, velocity going that way. We'll have another problem here for you in just a moment.